All right, ladies and gentlemen, here is our first lecture video of the year. What we're going to be talking about is experimental design. There may be instances when you are on the AP test where you have to either propose some elements of the design of an experiment, or you have to judge whether another experiment is going to be producing valid results or if there are flaws in the experimental design. So let's go over a few things. I found over the years that the best way to teach this is to go through a hypothetical example. So we're going to use this situation as our example for how we would set things up during an experiment um, throughout the entire lesson. So let's say that somebody has an observation that a person poured soda on a plant and then the plant died soon after. You want to know why this happened. So you have to pick one thing about soda that you think might be what harms the plant. So you're going to hypothesize that carbonation in the soda, the carbon dioxide that's dissolved in it, is what kills the plant. And what you want to do is now think, how would you test this? What experimental groups would you use? What conditions should stay the same? What conditions should change? And then you need to think about, what are you measuring? How should you measure it? And when should you measure it? And all of these are considerations that you'll need to make when you're deciding how you're going to test your hypothesis. So for this experiment, for any experiment, you need to have at least two groups of subjects. One is your experimental group, where you are changing some variable, where you are giving some treatment. And the other group is your control group. It's your baseline that you're making your comparison to. Your experiment always has to have at least two groups because you need to be able to make comparisons. You need to be able to say, this causes different data, or this produces different data than this other group. So what are our treatments going to be? Well, our hypothesis focuses on carbonation. So let's say that we're going to give one group of plants carbonated water and see what that does. Now, we need to have a control group. So our variable is carbonated water. We want to compare it to some baseline. Well, what do you usually give plants? Or what is a treatment you can give that does not have this independent variable? You can't just say, we're not going to give it water at all, because you don't know if what's causing the difference in results is the fact that you don't have carbonation or the fact that you don't have water. So what you can do is you can give water, but give plain water. Don't give carbonated water. And then you can judge how this affects the plant's growth or whether or not it kills the plants. Now, other than the carbonation of the water, everything else needs to be identical between the two groups. You need the same soil, ideally the same volume pot, the same volume of water given to them, and the same timing. If you give one plant water in the morning, you've got to give the other plant water at the same time. You need to keep them at the same temperature and have the same levels of sunlight. So for example, let's say that you grew the plain water plant in a part of the room that's not getting as much sunlight. Well, if you get different results, how do you know that it's due to the carbonation and not due to the difference in sunlight? You want everything else to be identical so that you can legitimately make a claim that, hey, the differences that I've got in my data between these two groups is due to this one thing and this one thing alone. Because you're trying to identify what factors are affecting your results. And if you do not have these, what we call constants, where you're maintaining everything the same except for the one variable you're changing, then you're going to have no idea what is causing your results. So let's talk about independent and dependent variables. There's multiple ways to keep track of these, and we'll talk about that throughout the year. But at its basic, kind of most simple, the independent variable is the variable you're testing. That is something that you as the experimenter determine. So for example, when I say that you can, as the experimenter, determine the intervals, you could decide, okay, I'm going to give carbonated water and I'm going to give plain water. Or you could create your own concentrations of carbonated water. So you could say, okay, I'm going to try different levels of carbonation and see how that affects things. So starting with zero carbonation, which would be your plain water, maybe 5% carbonation, 10%, 15%, so that you can also see what concentration of carbonation affects the growth of plants. That might be a good follow-up experiment. Here, we're just trying to see, does carbonation affect the growth of plants? Very common independent variable is time. So we're going to take these measurements at this time, or every 3 hours, or every 5 days. The dependent variable is the variable that you're measuring, and it is the data that you're collecting. If you can identify what data you're collecting, that will tell you what your dependent variable is. So for our experiment, what are our independent and dependent variables? So very quickly, you have space in your notes to write down where the independent and what the independent and dependent variables are for our experiment. So please pause this video and try and think of this on your own. This way, you can see whether you are thinking in the right way about independent and dependent variables, or whether you need more and more fuller and better explanations. That way, you can ask questions when we're in class. So pause. All right, hopefully you paused and are now resuming. So for our experiment, our independent variable is that carbonation of water, carbonating versus not carbonating. Our dependent variable, since it's not really easy to measure whether carbonation kills plants, what might be a better way to measure this is to measure how tall the plants are growing. So if you can say that carbonated plants have a very slow growth or don't grow at all, that will give you results that will give you just as much valid information as if you're like, oh, does the plant die? In fact, it's a little more valid. When possible, it's good to have numbers, data that you can quantify. It also lets you see trends like over time. For example, if you're measuring the growth of the plant every day, and if your only thing you're collecting is this plant alive or dead, you can't picture the nuances. Like, is the carbonation not killing the plant but slowing its growth down? Is the carbonation not keeping the plant alive but speeding the growth up? So it's very good to make sure that you have something you can measure. It's not always possible, but if you have the choice in your experimental design, pick a variable that you can measure numerically, because then you can do statistical calculations. So this is a good way that I've heard to remember the difference between the two variables, as well as what axes you graph them on. Because if we have a free response question where you have to graph, one whole point out of a potential 3 or 4 or 10 points that that question is worth will be, did you label the axes correctly? Did you graph correctly on the correct axes? So that's an easy point to earn, but it's also an easy point to lose if you don't do this right. So what does this stand for? I tell people to remember dry mix. The D in dry mix stands for dependent. Notice that D fits along that y-axis going up and down, so that should help you remember where to associate it. The R stands for the fact that it's responsive. It responds to the changes in the other variable. And then the Y stands for the fact that it is graphed on the Y-axis. As for the mix part of this, notice mix is attached itself to the X-axis. The M stands for manipulated. This is the variable that you as the experimenter are going to design. The I stands for independent. It's the independent variable. And the X stands for the fact that you show this on the X-axis. And we'll have more information about graphing in a separate lesson. So what is the difference between a control versus a constant? This is a question that I get quite often. Your control is an entire group of subjects, of organisms, of test subjects that you are using as a baseline for comparison to your experimental group. Constants are things in both groups, and these are conditions that you keep the same for both groups. So hopefully that does a little clarifying. We'll try and identify constants and control groups in experiments that we are doing. So we have to get into hypotheses now. And yes, I know it looks like I misspelled hypothesis. That's actually the correct plural of it. when you are writing hypotheses, generally the best form that I've seen that's recommended for you guys to write your hypotheses in is to write them in the if-then format. So you're stating if, and then you describe how you're manipulating the independent variable, then, and then you describe what change you expect in the dependent variable. So for our experiment, we could say, if treated with carbonated water, plants will grow less tall than plants treated with plain water, or plants will experience less growth than plants treated with plain water. Now, just like everything else in science and probably life, it tends to get more complicated as you go further. So there is not just one type of hypothesis. There are multiple types of hypotheses, and there are hypotheses that you're going to have to create that are different from what you're used to. The big one is what's called a null hypothesis. A null hypothesis, I think of the null as saying this doesn't matter. It's like nullified. Another website that I found when I was trying to find good ways to explain this to y'all said that the null is usually some commonly accepted fact that the researchers are trying to disprove. And it states what will happen or what results you will get if the independent variable and the dependent variable have no relationship, and manipulating the independent variable has no effect on the dependent variable. The purpose of a null hypothesis is it helps to validate your results. You're not only trying to provide evidence to support your ideas, but you also want to provide evidence that's going to um, disprove or that's going to not prove the opposite of your hypothesis. So usually the best experiments out there will try and design an experiment that will reject or kind of disprove or provide evidence against a null hypothesis. And then researchers will generally create an alternate hypothesis that will explain the results of the experiment and is usually what hypothesis you choose if you reject a null hypothesis. And we'll talk about this in more detail, and we will continue to talk about null hypotheses over time. So I mentioned an alternate hypothesis. The alternate hypothesis is the opposite of the null hypothesis. So in the null hypothesis, you say these two variables have no relationship. In the alternate hypothesis, you say these two variables do have a relationship, and this is how the independent affects the dependent. It also is letting you see, is there a statistically significant difference between the data from your experimental and your control groups to let you reject the null hypothesis. And usually this is the hypothesis that we're traditionally used to forming for an experiment, that if-then statement. And it's usually going to be the hypothesis that is tested by the experiment. So let's look at an example. And by the way, if you want to see this example in more detail, I have included the website, a link to the website or the website itself, address, at the bottom of the screen, which is where I got this example from, and some information about the null hypothesis. So let's start with the null hypothesis. The world is flat. We had a big revolution during, like the I think it was the end of the Renaissance or so, where a lot of scientists were trying to provide work to prove that the Earth is not flat. And some scientists were trying to prove that the Earth is flat. So the generally accepted information was that the world was flat. There was an alternate hypothesis, though, that the world is round, or that the world is a sphere. So many scientists, notable among them Copernicus, were working to disprove this null hypothesis, to disprove the fact that the world is flat. So they gathered data, and they, a lot of it was mathematical calculations, and these results were able to not only reject the null hypothesis, but provide evidence to help support the alternate hypothesis. And it's kind of makes sense when you think about it. If you want to change people's thinking or thoughts about a subject, usually it helps if you can disprove what they were thinking. If you think about a person who is a current flat earther and you want to try and convince them that the world is round, one of the first things you might do is try to provide evidence that the world is not flat. So for our experiment, our null hypothesis should state that there is no relationship between our dependent and independent variables. Basically, carbonated water should not affect plant growth. So if we state that as an if-then statement, if treated with carbonated water, then plants will experience the same growth as plants treated with plain water. Our alternate hypothesis was the one we formulated at the beginning. If treated with carbonated water, plants will grow less tall than plants treated with plain water. So what results would we expect if our null hypothesis was supported by our data versus our alternative hypothesis? If our null hypothesis is the one that we are supporting with our data, we would expect to see the same growth in both groups of plants, or perhaps even a higher growth with our carbonated water group. If the null hypothesis was rejected and you were accepting the alternate hypothesis, then what you would see is different growth between the two plant groups. You would see perhaps normal growth in the control group and very little to no growth in the experimental group. It's always useful to try and think when you're designing an experiment about what results you would expect to help reject your null hypothesis or to reject your alternate hypothesis. You may not always get results that fit either of those situations, but it kind of helps you to refine your experimental design. Speaking of which, a lot of times you'll be asked to evaluate the experimental design that they describe in a question. And so you'll want to ask yourself, are all these conditions met? And this list is not completely exhaustive. There's other things that you can do that you can ask yourself to see if it's a valid experimental design. And we'll talk about those as they come up throughout the year. So you want to make sure that only one variable is changed between the experimental and the control group. For our example, the only thing that was changed was carbonation. What we could have done, we could have said, okay, I'm going to carbonate one, give one carbonated water, and I'm going to give the other no water. Well, that would be changing two variables, the carbonation and the water. The control group does not have that independent variable manipulated. It's a baseline. It's like the normal condition you're comparing to. And that, in our case, was the plain water group. It didn't have that independent variable, which was our carbonation. Every condition except the independent variable has to be kept the same. That's the way you know that this difference that you're seeing is only due to that independent variable. So in our case, we would keep the plants probably growing in the same area with the same light exposure, under the same temperature conditions, given the same volume of water, given the same nutrients and soil and all of that. So that way, if there is a difference in their growth, we can say with pretty great certainty that, yeah, this difference in growth is due to the carbonation. And then finally, you want to take measurements at appropriate intervals. So for some of these experiments where you're kind of measuring things over time, what's the appropriate time scale? Do I want to measure every minute? Is that practical for measuring the growth of plants? Not really. What about every hour? Is that going to be practical for the growth of plants? It's more practical than any minute, but it's still going to be a lot more data than you probably need. For the growth of plants, most people, if they're like fast growing plants, will do like a measurement a day. And you would have to make sure you do your measurements at the same time every day. For some slower growing species like trees, you might do once a week, once a month. There are some experiments that we'll talk about that look at changes in populations over generations when looking at evolution and natural selection. And for those, the appropriate time interval might be once a generation. So it depends on what results you're trying to see, and you need to take measurements so that you will get the maximum benefit of being able to see the changes without taking so many measurements that it's not practical to be able to keep up with it. Because while a lot of this stuff is hypothetical for your test, if you are designing these experiments in reality, you want to be able to take these measurements when you're saying you're going to. So for example, when I was in graduate school the first time, I had to do research on fruit flies. And those fruit flies, in order to meet the conditions of our experiment, had to be checked on every 12 hours, which meant no matter what day of the week it was, weekday or weekend. Every 12 hours, someone had to be in the lab to check those. And in some cases, I was in the lab at midnight on Saturday night to check those fruit flies. So that is the end of this first lesson. I will have a couple of links in the description to some statistics videos that might help you understand the null and alternate hypotheses. I will try and find some for the experimental design. And then the fill in the blank notes should already be uploaded in Google Classroom. All right, I will see you later.